This is the lecture for Chapter 12, Chem 102 on intermolecular forces, and this is just a list of some of the things that we've got to cover in this chapter. So, intermolecular forces are what hold ions and molecules together. Although we call them forces, we should first make sure that we know right from the start that the forces are electrical, based on positive and negative charges. Other types of forces are gravitational, nuclear, but these don't count here. In fact, essentially all of chemistry is based on electrical interactions. It's also true that essentially all substances are made of molecules and ions that attract each other. We know this because any substance will form a condensed physical state, such as a liquid or solid. If the molecules didn't attract each other, they would always be a gas. Since we know from kinetic molecular theory that molecules and ions warmer than absolute zero always have kinetic energy, the energy of motion. And this motion pulls molecules apart. To form a liquid or a solid, the molecules and ions would have to have electrical attractions stronger than the kinetic energy, which causes repulsions. So what do we learn about the attractive energy from raising temperature? Like in this slide, kinetic molecular theory says that kinetic energy increases with temperature. So starting out cold enough, anything will be solid. The molecules are stuck right next to each other and can't move from their position in the solid. But the more you heat it, the more they shake. When the kinetic repulsion energy is similar to the electrical attraction energy, the substance melts, and we call this temperature the melting point. Now the molecules or ions break apart and mingle freely with their neighbors in the liquid, and if you keep heating, the substance will boil at a temperature called the boiling point. There, the kinetic repulsion becomes definitely greater than the electrical attraction, and the molecules and ions fly apart from each other. This model is used to compare the strength of intermolecular attractions. Imagine that our classroom at about 21 degrees Celsius, and all the molecules in the room at the same temperature, so they have the same kinetic energy. Water in this room is liquid, so its molecular attractions about equal the kinetic repulsion energy, while the air is a gas. while the air is a gas, so its molecular attractions are much less than the kinetic repulsion energy. Also, glassware in your drawer is a solid, so its molecular attractions are way more than the kinetic repulsion energy. We see that physical states give a crude comparison of intermolecular attractions. Solids are stronger attracted intermolecularly, liquids are less, and gases are less than liquids. We also use boiling points. For example, a gas at 21 degrees has a boiling point lower than a liquid. So the lower boiling point, the weaker the intermolecular attraction. Air molecules have weaker attraction than water. But what about air and natural gas? Both are gases at room temperature, but air boils at between negative 183 Celsius and negative 196, while methane boils at negative 161 degrees Celsius, higher in temperature. Air has the weaker intermolecular attractions because it has a lower boiling point. We also use melting points. For example, a liquid at 21 degrees has a lower melting point than a solid. So the lower the melting point, the weaker the intermolecular attractions. Water molecules have a weaker attraction than glass. But what about glass and plastic? They're both solids, but glass melts at 1500 degrees and plastic melts at 150 degrees. Plastic has weaker intermolecular attractions with melting points and with boiling points. The lower the melting point or boiling point, the weaker the intermolecular attraction. So this slide just shows, brings up the point that in this chapter we'll look exclusively at attractions between molecules. These are called intermolecular attractions. Excuse me. Intramolecular attractions are those holding atoms together within a molecule, like a covalent bond. Intermolecular attractions are much weaker than intramolecular attractions, intramolecular, and are often called weak bonds. So let's look at different types of electrical properties of atoms and molecules. Ions have full positive or negative charges, +1, +2, +3, etc., or maybe -1, -2, -3, etc. They're made of metals and nonmetals, and the metal is always positively charged, a cation, the nonmetal negatively charged, an anion, and their values can often be predicted, the charge values, from their location on the periodic table. In compounds, they combine in ratios that cancel out the charges. Polyatomic ions can also be used instead of a single metal or a single nonmetal. We've seen these before. And so we still need to be aware of what carbonate is, nitrate, sulfate, phosphate, ammonium, and hydroxide ions. And keep in mind that ammonium is a +1 ion, and so it can substitute for a metal in an ionic compound. Soluble ionic compounds have the property of being electrolytes. Dipoles are covalent bonds connecting different atoms within a molecule. All atoms have a property called electronegativity, which is a measure of how tightly the atom attracts the shared electrons in a covalent bond in a molecule. This causes the shared electrons to shift toward the atom with a higher electronegativity. This gives a partial charge, positive charge to the less electronegative atom, and a partial negative charge to the more electronegative atom. Notice the partial charges are denoted by a Greek letter delta. In any bond, you can tell the more and less electronegative atom because the trend for electronegativity is to increase from lower left to upper right of the periodic table. It's often helpful to remember that fluorine is the most electronegative and oxygen is number 2 of all the elements in the periodic table. So these atoms, oxygen and fluorine, are almost always the most electronegative in a bond. So in an oxygen-hydrogen bond, oxygen is more electronegative and therefore partially negative, while hydrogen is less electronegative and partially positive. Shown about are the partial positives and partial negatives for the atoms in several polar compounds. A special category of dipole bond is one that can form a hydrogen bond. This is a polar bond where one of the atoms is hydrogen, usually an OH or an NH bond. Although these partially positive and partially negative charges on the atoms in these bonds, the partial positive hydrogen is a much smaller atom than most of the other atoms that are in polar bonds and with dipolar interactions. And so the hydrogens with their positive charge, because they're so small, can approach the neighboring molecules more closely. This makes for an exceptionally strong dipole interaction. And here are some possible examples of where that might come into play. Nonpolar bonds are those with no charges like ions and not even partial charges like dipoles. So they interact differently than others. They have very weak interactions with their neighbors. These bonds are identify these bonds we can identify these bonds in that they have the same atoms connected together. Also, the carbon-hydrogen bond is also one that behaves as a nonpolar bond, and bonds in molecules where they are symmetrically distributed around a central atom are also behave as though they are nonpolar. In this way, the nonpolar bond, neither atom wins the fight for electrons. Also, molecules with symmetrical polar bonds cancel each other's charges, and they behave as though they are uncharged. So how can a molecule with nonpolar bonds ever bind to other molecules if they have no charges? The answer is induced dipoles. Induced dipoles occur whenever a neutral atom is approached by a charged atom or molecule. In this way, even the nonpolar molecules do have some weak electrical charges. So with different charges on molecules induce a series of charge interactions based on how large a charge is present on the molecule. We can see this affecting many properties of substances. For example, we can look at boiling points and melting points. Ionic compounds often have very high melting points, over 1,000 degrees. However, if you go to small polar molecules with small partial charges, the melting temperature is often below 0 degrees Celsius and the boiling point below 100. Heading to molecules with only induced dipoles, both boiling and melting points are well below 0. The attractions between molecules are all about number of weak interactions and the type. In this slide, I know it's not in your handouts, but it illustrates a point. Going across each row, we see the same number of carbons in the molecule, but 1 to 3 bonds are different. As the change position goes from lower charge to higher charge, the intermolecular attraction increased as seen by the boiling points of the molecule. Also, as you go down a column in this table, the number of nonpolar bonds increases. So the charge stays the same, but the number of charges increase. And so as the number of charges increase, the boiling point also increases. So we see an increase in intermolecular attraction based on the size of the charge on the molecule, as well as how big the molecule is, that is, how many contacts it can make with other molecules. So what are some examples of intermolecular attractions based on these charges? One is the hydration of ionic compounds. We see ionic compounds will dissolve in water, and the reason is we have the dipole attractions of the water molecule interacting with the charges on the ionic compound and breaking the ions apart by surrounding the ions with water. Moving on to the type of interactions where we have dipoles interacting with dipoles would be if we had a polar compound, not an ion, something like glycerol or an alcohol mixing with water, and those dipoles would interact with each other and dissolve. The picture of blue food coloring shows that there's a number of dipolar bonds that allow blue food coloring to be hydrated by water, which is a polar compound. Second on the list, the dispersion forces are when weaker charges are involved. One way to do that is a dipole compound. We call it a polar compound mixed with an induced dipole compound. Induced dipole compounds we call nonpolar. If we mix a polar and a nonpolar compounds together, for example, the organic compound hexane in water, they mix very poorly. The dipoles like to interact with each other, that is, water does, and the induced dipole compounds like hexane get pushed away from the water. So blue food coloring will not dissolve in water very well. On the other hand, if we have compounds that are based on induced dipoles interacting with induced dipoles, then they mix very well. In this case, hexane is a nonpolar compound. It has induced dipoles in its bonds. Will interact very well with the dye Sudan-4 because Sudan-4 also is a nonpolar compound and has induced dipole interactions. So this is about the halfway portion of the lecture. I'm going to stop it now and continue because I think it's a file size that I have to stop at.